had a good weekend. Um, so today, as I mentioned in my email last night, what I thought I would do is just spend a little bit of time going over um, the some of the problems from the sample problems that I put out last week. Um, and we can just kind of go through some of the solutions. A couple of them we may only set up the math, and then you could work it through to get the final numbers. In a couple places, I do actually have all the math worked out, but I'm just trying to think of what's possible in a 50-minute window. So what I'd like to do is I've set up a couple of slides for just some fundamentals, and then we'll as a couple of reminders, and then we'll jump into working through some of the problems. The other thing I wanted to let you know is, and this will be repeated, I'll just talk about the exam here for a moment, the end of this slide and on to the next. I created I think it's a 7-page document that's this conversions and constants sheet. It actually might be the 8, but anyway, all I did was just to create this, just so you know what's on there. It's available on the midterm preparation module right now on the homepage for Canvas, and it'll show up in a couple of places. I would advise you to download it and maybe print it out and just have it ready for you to look stuff up from, or at least have it open electronically to refer to. It basically has all the tables that you've been using over the past 5 weeks. I just copied those from the back of your electronic book. I did a screen capture, popped them into here. And so the first page is all a bunch of conversions, length, area, volume conversions. The second, third, and fourth pages. Oh yeah, maybe this is only 4 pages long. Anyway, those 3 pages are different tables where I then matched, let's just say, the properties of air, standard properties of air at different temperatures. Those are provided 2 on a page. One is BGS and one is SI. Okay, so those are available to you. And then the very last page has a figure from your book with the all of the moments of inertia for different shapes. Okay, so all of that is just reference material. The only thing that I did not include in there, although I take that back. Actually, it's in one of the standard tables for water, is the density of water. If you always just assume rho water is 1,000 kilograms per cubic meter, you should be good to go. Unless there's a question about water density at different temperatures or something like that. But in general, for the types of problems you expect to see, assuming 1,000 kilograms per cubic meter should be fine. Real quick then, the way this is going to work when you get to the exam tomorrow, and I will send you an email about this with all these details later tonight, but essentially you'll go to the assignments part of Canvas, and you'll see an exams little module. And it's not available now, but midterm 1 will be there. And then I can't find a way for you to submit something to the same place where you're going to put your answers and work through the exam itself. So I created this other assignment essentially, but the only thing you do is, it's not going to be graded at all. It'll show whether you've done it or not, but all you're going to do is whatever PDF work you do, whether you write and take a picture of it, or you whether that's hard copy or whatever, the PDF of whatever you do can be submitted there. Okay, so that will become, you won't see this yet either until tomorrow. But anyway, this is just the place to submit that. I think it does show up in the gradebook as binary, you either did it or you didn't, which is fine. That's not a big deal. The other thing I will say is that you don't need to submit your work within the 90 minutes that you have to work on the exam. You can submit it right after. So I'll give you an extra half hour on that just to be able to submit that. The midterm 1, though, when you click on it, it will have these instructions. So complete the exam online, the answers submitted to that part of it. And then here's another link to this this file that has all of the stuff. So this is not a different link than the one I'm giving you. It's the same document, but you can download it now if you want. And like I said, it's in I think it's called Midterm 1 Preparation module on the front page. That'll be the same file as this link. And so you'll have that available to you. All right. Any questions on that? If anything comes up in the chat, I think Emma and Alexi can handle it. Yeah, Emma, did you have something you wanted to interject?
Yeah, someone was asking, I know we went over this a little bit, but could you go over again how the exam is split up and like your multiple choice and free response sections and how many questions there'll probably be?
I don't have a number of questions yet, but it will be some amount of like multiple choice, some amount of like fill in the blank, some amount of like true false or something like that. I'm going to try not to, I don't want you to waste a lot of time on that, but the other thing is that you may see for those, so the way we engineered the point spread throughout the entire semester is that each of the midterms are 100 points. And so you might see that like a fill in the blank question is 2 points. Like that seems a little weird, but the reason for that is that just trying to make like let's say I had 10 of those, then that's 20% of the exam. Right. So don't worry too much about the points. I mean, obviously, if you get it wrong, then you lose whatever that credit is. But I'm just trying to make sure that things get weighted appropriately throughout the exam. So let me see. So there will be some section at the beginning of some mixture of fill in the blank, multiple choice, true, false. Then the second section will be something short like set up this problem or identify this piece of this problem, something like that. And then the last section, I don't know how many of those there will be. Let's just say there are 5. I don't know, something like that. And then the last section will be 2 problems that you would have to work out. So like a manometer problem or a gate problem, something like that. Okay, so there will be 2 kind of longish problems. Everything else will be like, fairly short one way or another. I have to set this up in groups to be in question groups. This is just mechanics, but don't worry about it. I've not set it up so that you have to do one question at a time. So you should be able to scroll up and down all you want and go back to something. Just be aware that you can do that. I think that covers all of the sort of description of the exam at the moment. Other questions, Emma?
I mean, I know we've gone over this, but they do need to submit a PDF of their test afterwards, and that's how we're going to give them partial credit, right?
Yeah, so the partial credit will only come if you submit your work. Otherwise, we just grade the answers that you've submitted, which they might all be right. I mean, you take that chance without us being able to see your work to be able to give you any partial credit.
So we would only have to submit our work for the long answer questions?
Correct. Yeah. Sorry. That's a great question. Yeah. We don't need to see your work, obviously, for like a fill in the blank or anything like that. And we're not setting you up to have to submit something that you can't answer online. In other words, for the 2 long questions at the end, you will obviously get to an answer and enter that. We want to see your work to be able to give you partial credit, but for the other problems, yeah, you'll just answer them straight up. We don't need to see your work on those. Yeah, good question.
And as far as like difficulty goes, is it going to be comparable to the practice questions you posted on Canvas, or more closely to like our Wiley Plus homeworks?
I don't. Trying to decide which one of those is harder. I
personally thought the Wiley were a little more difficult.
Yeah, I think. Yeah, it's hard for me to say. I mean, I think you'll have. Well, I guess part of the challenge with the Wiley stuff is you're always going for a number, right? So when it comes to those last 2 problems, I suppose you could say those are like the Wiley problems. Everything else will have to be a little more conceptual or whatever, right? Like more like what you've seen partly at the beginning of the questions I provided for you on Friday.
Okay, and just to clarify, we're only submitting work for the second part of the exam.
Call it the third part, but yeah, just those last 2.
But only the workout problems.
Like exactly.
Okay.
Yep.
Okay.
Okay, so I will write an email to you all tonight to kind of remind you of all this and get it all summarized, just so we're all on the same page. But obviously, if you have any questions, please let me know if something comes up. One other thing to mention: I will be on the class Zoom meeting. I don't expect anyone else to be unless you have a question. So that's the way that you can ask me a question. Please don't hang out there if you have a question. And I answer it, just move on and disconnect and keep working, because once somebody else comes in, it might be a little unfair. What I might do actually is change our link to set up a room for you guys to come in and out, so I can control. So somebody could ask me a question without giving away to somebody else what the answer might be that they've gotten, something like that. All right. But I'll be a resource during that 12:30 to 2:30 period tomorrow. All right. Anything else? Okay. Terrific.
Someone on the chat was asking, will the exam be presented as a whole, or will we only see like one question at a time? I think he's like, they're asking.
No, it'll be a whole. You'll be able to go back and forth. So it's not one question at a time. You'll have you'll have to scroll up and down, but it'll all come at you at once. I hope that's not too intimidating, but I worry about Canvas limiting your ability to get back to something if I don't do it this way. So, all right, cool. Okay. There's a little bit of review. I think I have 4 slides at the beginning, so let me just run through these. Hopefully, this is common knowledge for everyone. You feel comfortable with it. If you don't, then that's why we're doing it. So. Remember manometers. Here's a simple YouTube manometer, but essentially when we talk about manometers, oops, trying to get my pen going here. That's fine. Okay, so remember that if we were working from A to, let's just call this B, we would work our way from here to here. We'd work from here to here, and then we know that this pressure is the same as this pressure over on the other side. And so pressures at the same elevation are the same. Oh, I got an extra hump in there, sorry. I can't erase it. For or if they're in the same fluid. And if you move vertically down, you put more fluid above you, so you have to increase pressure, right? And if you move vertically upward, you are putting more fluid below you, less above you, so you would decrease pressure in some way. Now, that might mean subtracting it or losing it, however you're tracking it in your problem, right? So if we were to look at the difference, essentially, if I asked you a question like the pressure, which pressure is greater, the pressure at B or the pressure at 3, you would say the pressure at 3, right? Because you would have had to have moved down through this column and pile up more of this gamma 2 gauge fluid above you to get to point number 3. Okay, so a question like that would be like the kind you would see in, one of the first 2 parts of the exam, something like, how does the pressure at 1 and 2 differ from each other? Greater than, less than, right? That kind of thing. Not necessarily a calculation, although it could be. Hydrostatics. We have talked about, so after we talked about pressures, we also talked about hydrostatics, where we said, hey, at all pressures at the same horizontal elevation, they're all going to be equal to each other. And yet pressure works in all directions the same way. The only thing about them is that we change pressure from a hydrostatic perspective when we move vertically. So if we were to look at the pressure distribution on the bottom of this tank, if that bottom is horizontal, then all of those pressures are identical. So the pressures down here are identical, all of these P's. If we want the total force that's acting as a result of that, remember we said that pressure has dimensions of force per unit area, or force per length squared, right? then we multiply that pressure by the area of the bottom of this tank, and that would give us a force, right? Now, the other thing that became a little more complicating was to start to think about these vertical distributions of pressure. So one of the fundamental things that we know is that the vertical distribution of pressure, it obviously increases as we go further down, as we move deeper into a fluid. And that change should be linear for the same fluid that we have. All right. So for a single fluid, we would have a single slope here that is controlled by gamma of the fluid. And the pressure at the bottom then is proportional to the depth of the fluid above that point. Okay. And that's true for all points through depth. So as we start to look at what's happening on a vertical face, we have to account for, let's just say we only care about this section, then we only care about some component of this, but the pressure is going to start here and go to there, right? That might be the region that we care about for one reason or another. Okay, so let's take that a step further. As soon as we start to think about these forces acting across these sloping, sort of mostly vertical situations, then we have to start thinking a little bit about the two things that are related to each other but are importantly different. All right, and one of those is where the center. Extra hump in there. Sorry, I can't erase it. At the pressure distribution on the bottom of this tank, if that bottom is horizontal, then all of those pressures are identical. So the pressures down here are identical, all of these P's. If we want the total force that's acting as a result of that, remember we said that pressure has dimensions of force per unit area, or force per length squared, right? Then we multiply that pressure by the area of the bottom of this tank, and that would give us a force, right? Now, the other thing that became a little more complicating was to start to think about these vertical distributions of pressure. So one of the fundamental things that we know is that the vertical distribution of pressure, it obviously increases as we go further down, as we move deeper into a fluid. And that change should be linear for the same fluid that we have. All right. So for a single fluid, we would have a single slope here that is controlled by gamma of the fluid. And the pressure at the bottom then is proportional to the depth of the fluid above that point. Okay. And that's true for all points through depth. So as we start to look at what's happening on a vertical face, we have to account for, let's just say we only care about this section, then we only care about some component of this, but the pressure is going to start here and go to there, right? That might be the region that we care about for one reason or another. Okay, so let's take that a step further. As soon as we start to think about these forces acting across these sloping, sort of mostly vertical situations, then we have to start thinking a little bit about the two things that are related to each other but are importantly different. All right, and one of those is where the center of the area is for the shape that we care about. So in this case, if we have this gate down here, right, then the pressure that's acting on that gate is the average of the pressure between this location and this location. So some, P top and P bottom of the gate. Now recognize that, of course, there is some, the pressures at those two locations are dependent on the depth to get to those locations, right? So here's some H, let's call it up, and here's some H bottom, right? B for bottom of the gate. And those, what's important about those is those are vertical, right? Those depths are vertical, and you come straight down from the water or fluid surface in this case. However, and so we use those pressures and say, all right, what's their distribution across the shape? How do I add that up and figure out a force? So the magnitude of FR is pretty straightforward. So this depth range, we determine FR using the depth range, of interest, which might be defined by the depth range of the gate in this case. We also use the specific weight of the fluid. In which the gate is submerged, and we also use the area of the gate in this case, right? So we've said that FR then is equal to some gamma of our fluid times H sub C, which is the depth of the centroid of our shape multiplied by the area of that gate. Okay. So when it comes to just figuring out how much pressure we have distributed and what force we get out of that, we're using the pressure range for the depth range of the gate and the shape of the gate to get the area, right? And we just use the average depth of that shape, all right, to figure out this H sub C. When we determine the line of action, that's a little bit different. Now we are on the outside of this and we are looking from this point down. We calculate Y sub C to get down to the centroid of the shape, but that's not where the line of action is. Because we have that increasing pressure with depth, FR actually acts a little bit deeper than that, all right? And the way we figure this out is to use this equation here, which I've kind of covered up. But we're going to calculate the distance to the centroid of the pressure acting on the gate. And that's Y sub C. But then we have we calculate the moment of inertia of the shape of the gate. Okay, and that is this I sub x c. Okay, so in this equation back here, we basically are calculating this y sub r. That is a distance, again, reference to this location down at which that that force is going to act. Okay, so the force. So when we calculate the total pressure that's acting and the force value itself, we're just looking at the, we work from the centroid, but when we're looking at the line of action for that force, it has to be a little bit further down along the outside of the gate. Now we took this one step further and talked about a simplifying assumption for rectangular areas when we have pressure on rectangular areas, and we started to use pressure prisms. So here's a pressure prism on the right, or on the left, pardon me. You can see that we start at zero pressure here at the surface, and we have the highest pressure down at the deepest point here. And we may only care about this pressure, range of pressure right here, from the top of this gate to the bottom of this gate. Okay. And when we are working with a vertical construct like this, we can just look at these two depths, H1 to H2, to sort of figure out that the centroid is going to be, the middle of the middle of those two, or the average of those two. And it turns out that, of course, FR would act a little bit deeper than the centroid, right? Now, on the other hand, if we take this and look at the pressure prism approach to it, we can also just calculate these areas, right? A triangular area here, a rectangular area over here, to basically figure out what those the components of that force are going to be based on the rectangle and the triangle here of pressure that's acting for these two, and add them up to get an F1 and an F2 that would give us FR. Okay, so that was one simplifying approach where F1 and F2 are going to act at different locations simply because they represent two different things. One is all the pressure from above, which is basically the rectangle, and then the increasing pressure from below, or as we move down through depth, would be the triangle that's added on to that same location. Okay, with that, then I want to depart and go through some of these problems to talk about them a little bit. All right, so this isn't a great picture on the right-hand side, but essentially you can see that we have some sort of tank and we have two different fluids that are stacked on top of each other. Of course, the upper one has a lower specific gravity than the lower one. And so they have separated in this way. So the question is simply that the pressure above the free surface is zero. Sketch the pressure prism acting along the right side of the tank and explain your choice of distribution. Now, I'm going to do this in a sort of qualitative manner. And the first thing I'm going to do is just draw, as you would expect, some increasing pressure prism that starts at 0 and has a maximum at this interface for fluid 1 and fluid 2. Remember that the specific gravity, of course, is equal to the specific weight of your fluid divided by the specific weight of water, and the specific weight of water, or any specific weight, is the density of your fluid multiplied by gamma, right? So this is rho W gamma, all right? So what's happening here then is when we go from a specific gravity of 0.6 to 1.5, what that means is that we are increasing density substantially, right? And when we do that, we're also increasing our specific weight. All right. So what I'm going to do then is just simply draw this transition to indicate a bigger slope. All right. So this was kind of steep. This is now less steep because we are increasing pressure faster with depth now. And the reason we're doing that is because gamma 2, it dictates this change, or that rate. Gamma 1 dictates that one, and gamma 2 is much greater than gamma 1, right? Because of this relationship. So the way to think about this then, so we're not going to ask you to draw this out on the exam because we can't look at a drawn response. But what we can do is provide some different if we were going to give you a problem like this, we would show different distributions and ask you to identify which one was the correct one based on the information given. And they would be somewhat subjective, right? I mean, you would have to look for this change in slope and that sort of thing. Does that make sense?
There's some questions.
Yep.
Yes. Okay, the most relevant to this is, can you explain why the slope isn't steeper for gamma 2, I assume?
Yeah, so the reason it's not steeper is because with this, I've drawn this shallow because we are increasing pressure faster, right? Remember that we're showing that these slopes are relative to the increase in pressure as you go down. And so the specific gravity of 2 is much greater than 1, and that's why these slopes look different.
And then can you explain really fast when you can use the YR equals 2/3 height rule? Or
yeah, going back to that, that's
just like the rules.
Yeah, let me just go back real quick. That's only for pressure prisms when you have a rectangular or square gate that you're looking at. I actually haven't derived this for a circle yet, but it just works out that the 2/3 rule for a pressure prism works out because you end up with that 1/12 AB cubed or whatever. That part of the I sub CX or XC, pardon me, the initial, the moment of inertia, just so works out that you end up with a 2/3 relationship there. So.
Is that only if the gate is like vertical? It can't be at an angle, right? Or is that always?
It can be. The problem is you have to just change your orientation, right? Let me think about that for a second. It should work Y sub R. The trick is it only works for the triangular piece. It doesn't work for the rectangular piece.
Oh, okay. Great.
Okay. So it works for the triangular piece. Oh, sorry, that wasn't a very straight line. It works for the triangular piece, and then it's only going to work over that range. So it can work. You just have to make sure that you're working with the right depth ranges.
For the rectangular piece, would FR act at the centroid?
Yep. Yeah, so that's what's indicated over here, this F1 that I drew over.
And then this is a little off topic, and I know the test isn't finished yet, but for those practice problems, that like long packet, is that like what people should expect for how long the test will be, or will the test be shorter?
No, I just collected those. I did not mean for that to look like an exam. I
Cool.
did not count those, so I just tried to provide you as much background as I could. So don't think that's indicative of length. Not that I'm saying I'm going to make it longer, but I wasn't thinking about length when I put that together.
Cool. And then Whitney, if you want to say your question out loud, I don't think I really know how to ask it correctly, or if it's still right.
So I think it was the slide before this. Is a line of action of S of R Y sub R?
Yes. So the
Okay.
distance to get to that line of action is Y sub R. Yep.
Okay, perfect. And then if it were asking for like the depth that it would be or something, that would be like an H value as opposed to like a Y.
Exactly. So let's say you figured this out and it was, 25 feet or something, right? And you knew what this angle was. You
Right.
can always take the sine of theta and sort of figure out, from a ratio what that depth should be for that. Just use a little bit of trig.
Okay, thank you.
You bet.
Okay, another test question. Will your problems have equations, or will students need to know the equation they need to use for a certain problem? Like have it?
So because this is open book and open note, you guys will have to have the equations. Now that said, the equations are going to be like this guy. They won't. I don't expect you to derive some new crazy equation. You'll be using the same set that we've been using for the past 5 weeks or so. But you will have, like, for example, to populate the moments of inertia, you'll have that handout that we're providing electronically. So does that help? Great. Okay. This problem is similar to the next one, and we're running a little low on time. So why don't I do the next one? Just because it's I'll lay this out real quick. This isn't too bad. So you have this 3 meter by 3 meter by 3 meter cube, and when you put it in water, in this case, it's like an iceberg. You get 2/3 of the height underwater, and a third, a meter of it sticking out of the top. So the question is, what is the specific weight of the cube? So we know that the weight of the cube is equal to the water that it displaces, right? That's how we get to this. This is how buoyancy works, right? So the weight of the cube is equal to the specific weight of the water multiplied by the volume of the water that the cube displaces. So I'm just going to call that V sub for submerged part of the cube. All right. So we know this. The question is, what is the volume that's submerged? So the submerged volume here is, remember, it still goes 3 meters back into the page or the screen here. So we have that 3 meters in, I don't know if we want to call that depth or width, depending on how you think about that. Then we multiply by 2 meters. that's submerged on this front side. And then we also multiply by, let's see, so that was I have another 2 meters here for what is submerged. Let's see.
No.
That's 3 meters, 2 meters. Oh, I guess I'm wrong. That should be another 3 meters across, shouldn't it? So that should be 3 by 2 by 3, right? So that comes out to what, 18 cubic meters? Right. So when we do that, then we can basically figure out the weight. This is where I'll just stop without having to do the entire problem, just to save a little bit of time. But you can now plug that in to this. You can look up the specific weight of water and figure out the weight of the cube. Oh, sorry. I guess it was asking for the specific weight of the cube. So this is to figure out the specific weight of the cube. Then we know its volume is volume of the cube, and we're gonna just take the weight of the cube divided by the volume of the cube in this case. Okay. Sorry, I thought we were just going for the weight, but we have to take this a step further. So you'll figure out the weight, and then in this case, the volume, of course, is just 3 by 3 by 3, so 27 cubic meters. All right, to work that one out. Okay. Now, this one is a little bit trickier in the sense that we need to break it up into 2 pieces. So in this case, we're displacing part of the cube is displacing water. The other part of the cube is displacing oil, right? So we know that it's 2 by 2 by 2 feet. Now we're not working in meters anymore. 2 by 2 by 2. And half of a foot here is displacing oil 1.5 feet in depth is displacing water. So when we work through this, we'll use gamma water, which is something we can look up, right, from the tables that you guys are provided. Gamma oil in this case is noted to be 0.91 of gamma water, so 91% of that. And then we basically work with, I'll do it on the next slide. I actually have a little more room. I provided us some room to work there. So on the next slide now, we would basically say that, let's see, we are going for determine the weight of the cube. Yep. Okay, so the weight of the cube would be equal to these 2 pieces that we have to put together. So the volume of the oil that is displaced times the specific weight of that oil plus the volume of the water that's displaced multiplied by the specific gravity or specific weight, of the water. All right. So essentially then it just comes down to a little bit of geometry. We already talked about what that the gamma oil is on the previous slide. The volume of the oil that is displaced, we said is half of a foot vertically, and then we still have 2 feet back and 2 feet on this side, right? So times 2 feet times 2 feet, right? And then the volume of the water that's displaced is 1.5 feet times 2 feet times 2 feet. Okay, so that's how you basically solve that, is to figure out, you remember that the gravitational force for these is their specific weight multiplied by their volume, right? Any questions on these that are popping up, Emma?
Just a fast one on the test. It's not ready yet, but do you know how much buoyancy will be on the exam? Like an idea of how much?
Couldn't tell you.
And stability. Will stability be on the exam?
Stability, we didn't really have any problems directly on stability in the sense of like a numerical problem. So don't worry too much about that. Like what would be the overturning couple you would need to resist or something like that. Instead, buoyancy would come in something like this. Stability would only come in like a multiple choice problem or something, kind of like you saw in the stuff I provided and the what's in the chapter is basically kind of basic. So basically kind of basic. I can't believe I just said that, but anyway.
I have a
Okay. Yeah. Was that another one?
two back, two behind. That one. So the volume of the cube, that would be like 3 times 3 times 3 times 3. You wouldn't. Okay. Not the submerged part.
No, in this case, when you have to get so you get the weight of the cube from working through the buoyancy part of it, the top part. But then to get the specific weight of the cube, you have to take that total weight divided by the total volume of the cube.
Yeah, because then you just get the water specifically.
Yeah.
Thank you.
Sure. Okay. Real quick, let's do a reef problem here. Okay, so in the system on the right here, we've got a hinged gate. It's hinged at the top. The top of that is 29 feet down, and then we have another 5 feet of the gate. Regardless of what the shape of the gate is, the question is for the average pressure acting on the gate is calculated as what? And I will add 2 things here real quick. One is that the depth of the water to the top of the gate is 25.1 feet, and the depth of the water to the bottom of the gate is 29.4. So we'll let this go for a minute, but the question is, what is the average pressure acting on the gate? Is it the pressure at 29 plus the pressure at 34 divided by 2? So this is 29 feet, and this is another 5, makes 34. Is it the pressure at 25.1 plus 29 divided by 2, pressure at 29 plus 29.4 divided by 2, or pressure at 25.1 plus 29.4 divided by 2? So take a moment to answer that. Remember that pressure only changes when we move through elevation. So the question is, which of these heights or depths is the right one to use? Okay, we've got 74 responses. Let's see, how many are online today? I can't seem to get my cursor to get over there. 92. Okay, we're up to 81. So I'll give you guys another couple seconds. This is going to be 0, but I'm going to, as we're answering this, I actually thought a little bit about this. The point of this was that these pressures were supposed to indicate the depth. These values were the depth of water that was indicated, right? And 29 and 5 in this case are not the depths of water, right? So the pressure at 29 is actually like somewhere in here-ish, and the pressure at 34 is somewhere way down here, right? Those are the wrong references. The right ones are the depth.
Sine 60 times 29, and that is 25.1. Nice. And then 29 34 sine 60 times 34, and that's 29.4. Okay, so this is a good question. Average pressure acting. Okay, take a picture of this.
to get to 25.1 or the top of the gate, and the depth to get to, in this case, the bottom of the gate being at 29.4. So good job. Good job. Well done. All right. Now, oops. Okay, great. That's up an arrow probably. I was afraid of this. All right. Where did my cursor go? There it is. All right. Here we go. Okay. So here's a manometer question. Basically, determine the specific weight of the unknown fluid in the figure. Both ends of the setup are open to the atmosphere. So this is open to the atmosphere. This is open to the atmosphere. And essentially, we can work through this system and try to figure out what this unknown fluid is, or at least its specific weight. Right? We don't quite know exactly what it is. If we can just characterize its specific weight, that'll put us on the right path. Now, remember that when we're working through these manometer problems, we're basically going to be working from, I'm going to start I'm going to call this 1, and we'll notice this is 2. Here's point number 3, and here's point number 4, right? And so to go from P1 to point number 2, we're going to have to add this pressure up that occurs. And when we do that, we just have to do a little bit of math to figure out these heights, because we're just given some of these heights. So this is going to be 0, but I'm going to keep it there as P1. We're going to add the height of the water here is 5.5 inches minus 1.4 inches. Right, that gets us to the interface with the unknown fluid at 2, and then we're going to multiply by gamma water to figure out what that pressure change is. Then to get over to the other side, note that, if we come over here, we're now looking at 3.3 minus 1.4 to figure out that height there, right? So now we're going to subtract, because we're going to go up in height here for our unknown fluid to the interface with the other water over here. So now we say we have 3.3 inches minus 1.4 just gives us that height to get to the interface, and we multiply by, I'm going to call it gamma question mark, right? That's our mystery fluid. And then we're going to go up in height to through this water. And so once again, we're going to say minus, and now we have 4.9 minus 3.3, right? To get this height right here, we say 4.9 inches minus 3.3 inches. And now we multiply by gamma water again. And that gets us to 0, right? The pressure at number 4. We could have called that P4. Now I started this with P1. In reality, this P1 is 0. It's atmospheric pressure. But what this allows us to do now is to now do some really simple math to just weight each one of these. So let's just do the math inside of each of these parentheses, and I'll just show you this simplifies fairly easily. So 5.5 minus 1.4 is 4.1 inches times gamma water minus, and then we have 3.3 minus 1.4, so that's 1.9 inches times gamma question mark. Oops, that should be a question mark. And then we have minus 4.9 minus 3.3 is 1.6 inches, and we multiply by gamma W, okay, equals 0. So now what we can do is group them and basically put the gamma W's together, right? So 4.1 minus 1.6 gives us 2.5 inches gamma W. That would be equal to, I'm just going to move this guy out to the other side, 1.9 inches gamma question mark. And then we can take this one step further and simply say 2.5 divided by 1.9 gamma times gamma W is equal to gamma question mark. I lost my inches there, but they're going to cancel. The units will cancel. So that's essentially how you figure out, we could put in 62.4 here for gamma W and figure out what that value is. So it's something greater. 2.5 over 1.9 is obviously greater than 1, right? That ratio. So it's going to be something greater than water, which is kind of cool. All right. Emma, any questions coming up that we should address? Or Alexi?
No question in the chat. If there's time, there was just a question on the midterm sheet that a lot of people in office hours today had questions about, and we were trying to think through, but we weren't completely. It's with the curved surfaces underwater. And I have it open. I can share the screen if you want, but a lot of people are stumped by that, and I wasn't exactly sure either. So I wonder if that's like a good thing to go over.
Okay, I didn't put that in my my sort of problems here. So do you want to share it real quick?
Yeah. Just give me 1 second. I have it.
Okay. The idea with these is to try to quiz the difference between where the line of action would occur and how the pressure is distributed. Okay, so real quick, the other thing to note is that in a bulk sense, these have to be hydrostatic, right? So the horizontal component of the hydrostatic force on the left surface is what compared to the horizontal component of the hydrostatic force on the right surface, depicted with these arrows. So, assuming that both of these have the same radius, right? They're both there's no difference between these two radii. Is that right? I'm just reading the above. Yep, two curved surfaces. Yeah, same radius. Then those horizontal forces have to be identical to each other, right? Because the horizontal component, the change in pressure through depth is identical. As long as these two are at the same height, the same depth range, then the horizontal forces have to be identical to each other and opposing each other, and then they have to be the same on each side, essentially, or each of these two figures. Does that make sense?
And the problem also continues. It asks about the vertical component forces. I guess I can try to get it. I think most people understood that, but people were most concerned about the vertical forces being whether they were equal between the two.
Okay, so for each shape, so take the left one by itself, take the right one by itself. Those vertical forces on each shape individually have to be in balance with each other. Okay, so that part should make sense. But this is where the line of action part would become a little bit different. So if we were looking at now, when this is submerged underwater, it's fine to say that the verticals match each other top and bottom, but they might be different on the two forces. If we were to put these at the edge of a tank, let's say, the lines of action would be a bit different because of the distribution of pressure on one side compared to the other, right? And so you would add up. So while the pressure range is identical on both of these, because you have essentially think about it as different amounts of water over these on the sort of the left-hand side of each one, then you would end up with a reaction force that would be slightly different from these just because of the distribution of the forces. In this case, so sorry, Alexi, what are our options for the answers here? Did I include those on the next page? Equal to, less than. So it's phrased, the left surface is blank, then the vertical component of the hydrostatic force on the right surface as the dashed arrows. They have to be in balance with each other. Let's see. I guess you have, so on the left one, what you've done is because you scoop down, you end up with more water above that surface than the one on the right-hand side. So you could say that the left one is going to have a greater vertical component than the right one. But the verticals for each shape themselves should offset each other. So those have to be equal to each other. It's just that the left one would have a greater vertical component. No, Alexi. Sorry, it'd be the next one down. Yeah, if you were
Oh, sorry. I guess I can't.
Yeah, that was the horizontal question. Yeah.
Yeah. Sorry, I can't have it on the same screen. So yeah.
Yeah.
Oh, it's all messed up anyway. But
Oh man, they freeze. Oh, that's awful. Yeah.
oh, because it's like on the annotate, but it's greater than, I guess. Sorry.
It's like using whiteout on to fix your typing problems on a computer.
Yeah. All right. Thanks. There's a lot of people are confused by that.
You bet. Okay.
Professor, are you posting these tonight? The solution to this tonight?
I don't have solutions. I have my solutions that I'm working out for you guys, but I don't have a solution for all of the problems. So what I'm going through are the solutions for the problems that I picked out for preparation for tomorrow. Is that answer the question?
Yeah, there won't be another thing posted tonight with the solutions to all of the problems on the midterm practice.
No, I don't know. I guess I didn't prepare that, but I did work through the problems here, which is what we're doing now. So,
and you're posting this video tonight.
Yep.
Right?
As soon as it's ready. Okay, we're past 5. I'm going to keep going just to be able, because I have to film all of this anyway or video it. So if you want to drop off because you have something else you need to go do, this will be waiting for you after I post it on Canvas. But there are basically 1, 2, I guess 4 more problems that I'm going through. So you're welcome to stick around if you'd like. I'll just keep going. All right. Okay. Looks like I gave myself room to work that we didn't need. So, all right. Now, what about this question? For in this case, we have known fluids. We have an oil, we have mercury, we have water. The question is, in this YouTube manometer, if we have a pressure difference of 8 psi between A and B, the question is, oh, look at that. I did not work it out. Well, we'll do a little bit of working this out together. I don't know how I skipped this one in my notes, but the question then is, what is H going to be? Okay. So here's what I'm going to do. I'm going to work this out sort of longhand here. We're going to start at A. So there's a pressure at A. We know that to get from A to this interface right here, I'm going to call that 1. I'm going to call this 2. And then we get to B essentially. So PA to go down, I'm going to increase my pressure. So I add 6 inches plus 3 inches gets me to point number 1 there. So 9 inches times, in this case, gamma oil. And then we have, and we are not given that gamma, so we won't be able to solve this completely, but we can set it up. And then we need to go from point 1 to point 2, and we'll basically we will add pressure because we're decreasing our going deeper or decreasing our elevation within the same fluid. So now we have H times gamma mercury. So we'll indicate that Hg, and then we subtract H plus 3 inches gets us up to point B, and this is gamma water, and this is now equal to P sub B, right? So now we're given that this is 8.5 psi. This difference, the pressure in pipe A is 8.5 less than the pressure in B. So one of the things that we could do is just say PB minus 8.5 psi is now what we refer to as PA, and we can now work through this other, just basically. Let's see, I guess we can't collect terms, but I will note that we've got sort of this 9 inches times gamma oil again. We could look up a specific weight of oil, but we need a little more information. We said that we had multiplied by H times the specific weight of mercury, and then we'd have minus H. I'm going to just multiply this out, gamma W minus 3 inches times gamma W is equal to PB, and just note that we can basically get rid of PB on both sides. We still have this constant of 8.5 psi. We can move that to the right side. If we were given gamma oil, we can look up gamma Hg, we can look up gamma water. We could basically solve for H. Okay, so we have one equation with one unknown. We should be able to solve for H. We would just have to group these terms, and we'd have gamma W there as well. All right. So apologies, I don't know why I didn't have that one prepared, but that's basically how we would work through solving that one. Okay. All right. An exceptionally innovative bear is going to stick a hollow reed straw vertically into a pot of honey. And that's not shown at the right, but let's just take a straw. We don't know what its radius or diameter is, but it's going to go into a pot of honey. So here's our honey. It's going to go up some height, right, that we're given. In this case, we are given that this is 2 centimeters. It's equal to H. Sorry, I'll finish that. And we are given some information about the surface tension of honey, for example, and we are given that the density of honey is 36% greater than that of water. So rho sub H is equal to 1.36 times rho water, and what else here? Oh, and theta, this angle here, is 45 degrees, right? And if you go to your book or the notes, we related all of these things by basically saying that H is equal to 2 times the surface tension of the fluid. In this case, that's honey. Oops, honey. Times the cosine. Cosine of theta, and then we divide by the specific weight of honey, and also the radius of our reed in this case, right? And we also know that the diameter of the reed is equal to 2 times its radius. So if we can solve for R here, we can basically figure out what the diameter is, okay? So we're given some information. We're given that sigma, the surface tension of honey is equal to 0.062 newtons per meter, right? So we know that. We're given theta. We can figure out gamma H, because gamma H is equal to 1.36 times rho water times the acceleration due to gravity, right? So we can plug that in here as well, and we're given that H is a rise of 2 centimeters, okay? When you work this out, I get an R equal to, it's pretty small, 0, I don't know why I can't write a 0.3 millimeters. Okay, so the diameter then would be 0.6 millimeters. So just taking that and multiplying it by 2. All right. Next question then. Now we have a plate in the middle here. Maybe I should have made it a different color, but it's a plate that is in between these two fluids, and those two fluids have different heights to them, essentially, different thicknesses between the plate and these walls, okay? So a large movable plate is located between 2 large fixed plates as shown below, 2 Newtonian fluids having the viscosities indicated. So we have dynamic viscosity here and dynamic viscosity here, are contained between the plates. Determine the magnitude and direction of the shearing stresses that act on the fixed walls when the fluid plate has a velocity of 2.8 meters per second as shown, and assume the velocity distribution between the plates is linear. So what that means then is we go from zero velocity at the surface to a velocity of v at the middle plate, right? And the same thing over here, we have this increase. I shouldn't have made that bigger, but anyway, the idea is we're going from over 0.09 meters, so 9 millimeters, we're going from 0 to 2.8 for the top fluid, and at the bottom fluid, over 5 millimeters, we go from 0 to 2.8 meters per second. Okay, so some pretty strong. Remember, we're going to use this relationship. Tau is equal to mu du dy. That's the way it was written in your book. U is essentially here of velocity. All right. So and y is some height. All right. So when we say a linear distribution, we mean that we can go from zero velocity at zero height to 2.8 meters per second over 9 millimeters for the top, and on the bottom we would go from zero velocity at zero height up to 2.8 meters per second in 5 millimeters. Okay. Sorry, I keep saying millimeters. These are centimeters, aren't they? Sorry about that. But 9 centimeters and 5 centimeters. Okay, so real quick, let's just write these out then. So for fluid 1, tau 1 is equal to mu 1 times du dy 1 and 1, right? So whatever this velocity distribution is. So we are given that we have 0.03 Newton seconds per meter squared. And now we basically go from 2.8 meters per second minus 0 divided by 0.09 meters, so 9 centimeters minus 0, right? And this comes out to, if you do this math, you get 0.93 newtons per meter squared for tau 1. And so that is the shear stress that is essentially acting on the top wall here, the fixed one, very top. And then secondly, we figure out tau 2 is equal to, now we have mu2, the viscosity, the dynamic viscosity of fluid number 2, times du2 dy2, and this is equal to 0.01 Newton seconds per meter squared, times, now we have a velocity distribution that goes from 2.8 meters per second to 0 over a distance of 0.05 meters or 5 centimeters from 0, right? And when you do this math, you come up with 0.56 newtons per meter squared. Okay, so this is essentially, this T2, tau 2, pardon me, is the shear stress acting on the bottom fixed wall, all right? And in both of these cases, these shear stresses are essentially acting in the opposite direction of the movement, just providing this resistance that's there.
Is it true that the shearing stress is always opposite of the direction of the plate?
In this case, I hesitate to say always because I'm trying to think of the exception, but in general, yeah, it's the resistance to movement. right? And so when things are moving in one direction, the shear stress is usually acting in the opposite direction. I suppose you could have a case where you put something into a moving fluid that was moving slightly slower, and so it could be in the same direction, but it would be just a slower. Well, no, that would probably be acting in the opposite direction as well. Yeah. Sorry, Elizabeth, you got me on the always. I always try to think about the exception to the rule, but in general, yeah. Okay. So the last question I have. So here's another quicker question. We won't do it because we're after 5 and people have probably dropped off. But the question is, if the diagram in this diagram on the right, where does FR act along the wall compared to point A? So I just put A at the top. And so the question A, or the answer A here is, does it act within this range? B is saying, does it act within this range? C is asking, does it act in this range? And D is basically asking if it acts somewhere down here. Okay.
Yeah, C.
And the answer, as most of you are probably already thinking, is that it has to be past the centroid, which would be 3 feet, 10 plus 3 would be here, but it's got to be past the centroid, but it won't be past the bottom of the gate. So it's going to be in this range here, which means that that C is the right answer here, somewhere between the 13 and 16 feet measured along the wall from A. So this is not depth, right? We were talking about depth H. We would come from the top down from the water surface vertically. We're working along the length of the wall here. Okay. So the question that we're about to answer or work on, there goes depth, comes from essentially the same dimensions. All right. So if we have this situation, so instead of green, now it's a pink hue and red. The question is, if for a rectangular gate with a width of 4 meters, so it's going into the page, 4 meters here, 4 feet. If it's located on this sloped side of a tank, if the weight of it is 8,000 pounds and it's held in by some force P, ultimately we get down to part D asking what is the magnitude of P that will hold this gate in place. So we are asked A, to draw a free body diagram and label the forces, B, calculate the magnitude of the resultant force, so FR, and then C, determine the distance at which the resultant force acts on the gate from the hinge, and then finally calculate the magnitude of force P that will hold the gate in place. All right, so let's add this up kind of one piece at a time. So let's start with, here's my rendition of the gate. It'll have the hinge at the top. It'll have some length to it, some thickness. And we said that it has some weight, 8,000 pounds, right? The weight is going to act at the centroid, of course. So there's W acting in the vertical direction. We said that we were given in the drawing that we have some force P acting down at this end to hold it in place. And then the other force that's acting, we don't know exactly where it is, but I'm just going to draw it down into the left of W at the centroid, is some resultant force of the pressure, of the hydrostatic pressure acting from the overlying water, right? So those are basically our 3 forces, right? And you can see that none of them, well, I guess weight is acting purely in the vertical direction, but otherwise P and FR have horizontal and vertical components to them. Okay, so that's pretty straightforward. Part B then asks us to calculate the magnitude of the resultant hydrostatic force on the gate. All right, so recall that this is the general equation we've been using. The resultant, this hydrostatic force, F sub R, we've been calling it, is equal to gamma W times the height or the depth rather of the centroid of our shape of the gate in this case, multiplied by the area of the gate, right? So one thing I want to point out, this is just giving us the average pressure acting on the gate. When we multiply out by an area, we get a force, right? So now what we need to do is figure out if this is our centroid. Oop, that was not a very straight line, but basically what is h sub c to get to that center point. Now that center point, the centroid, should be halfway along the length here, right? So it should be 3 feet from this end. Okay, so that means it's 13 feet from the top here, and we were given that it has a 60-degree angle to it. So the question is, what is h sub c? Well, the sine of 60 degrees, oops, I wanted to write theta, 60 degrees is equal to, you know what? That is not the sine, that's the cosine. Sorry, did my trig wrong. Cosine of 60 degrees is equal to h sub c over 13 feet.
No.
Okay, so all we're looking for is we've got a hypotenuse that is this length, 10 plus 3, halfway down the length of the gate.
No.
That's where we get 13 from. H sub c is going to be adjacent over hypotenuse, gives us this relationship for cosine of 60 degrees. Okay, so we can figure out h sub c. And I did my math wrong because I did this with sine by accident. So,
are you sure it's not sine? Wouldn't it be the portion that's like going down opposite of 60 if you draw your triangle?
Oh, you're right. This is now. No, wait. Oh, you're right. This is now 60. This is theta. Thank you. I did do it right. Or did I? No, actually, I'm not feeling confident. But anyway, this is, so if this is 60, this is 60, which means this is 30. So it's either the cosine of 30 or the opposite over hypotenuse for this guy would be the sine of 60. So thanks. I don't know who said that. So, but you're correct. This is the sine of 60. Okay. So I did do it right the first time. Okay.
Be nice and easy.
So when you do that calculation, you end up with 11.26 feet of depth. Okay, so that's where we are depth-wise, h sub c. So thanks for that. So we can look this up. Of course, it's going to be 62.4 pounds per cubic foot. We just figured out h sub c, which we can plug in there. And then the area of the gate, of course, is, we said it was rectangular. So it's 4 feet wide or into the page times 6 feet in height. So this comes out to 24 feet squared. Okay, so now you've got what you need. If we solve this real quick, FR is equal to 62.4 pounds per foot cubed times 11.26 feet times 24 square feet. We get 16,860 pounds. Now, you'll note that to get here, we did have only one significant figure here. That gave us something with two significant figures. Based on what we have here, I'm going to go with two significant figures. That would give us, we'd be rounding this up to basically 17,000 pounds, right, is approximately what FR is then in this case with significant figures. Okay, now part C is to determine the distance where FR acts. Remember, we said it's going to be below the centroid. And so the question is, what is FR? We've figured out FR. What is Y sub R? Some length to get down to that point. So I'm going to do that on the next slide. Y sub R, we go back to our fundamentals, we said is Y sub C plus IXC over Y sub C times A, right? So this would take us to the centroid, and then we add a little bit more based on the physics of the situation and the distribution of pressure on this rectangular area. So y sub c will take us to the midpoint here. We said that that is 13 feet. It's 10 plus half of 6. So that's y sub c. And then y sub r is going to be something down here that we need to calculate. So there's y sub r. Okay, so y sub r is equal to, we said y sub c is 13 feet. And then our moment of, is there a question? Well, okay, our moment of inertia would be equal to 1/12. And in this case, we have b times a cubed. B is the height of our, or sorry, the width of our rectangle, and a is the height. So this is going to be equal to 1/12 times 4 feet, and then multiplied by 6 feet, and that quantity cubed. So this is going to be equal to 72. We do this math. Feet cubed. Sorry, to the fourth, beyond cubed. All right. So over here, then we would end up with, 13 feet plus 72 feet to the fourth power divided by 13 feet. Sorry, this should be a plus. Almost looks like a 4. 13 feet times, and then we add, I know we did it on the previous slide, but basically 6 feet times 4 feet area, right? 24 square feet. When we work that out, we basically end up with 13 feet plus 0.23 feet. So y sub r is just barely greater than 13. It's 13.23 feet.
Yes.
Right? So that's not huge, but where it becomes important is in the next step. To figure out what the magnitude of P is, we go back to our diagram, our force body diagram, and we figure out the moments. All right? So the magnitude of the force P that holds the gate in place, we take the sum of the moments about the hinge. We know that they have to equal 0 for this to be hydrostatic. So we then basically work out these three forces. So we say this is equal to, we have P acting at 6 feet away. So P times 6 feet. And that is going to be positive or negative. If I do my right hand rule, that ends up being negative. These just have to be opposite of each other. You just have to get the sign correct, or as long as they're opposite of each other, they have to be relatively correct to each other. So that's right hand rule tells me that's negative. FR on the other hand is going to be positive. So now we have FR, and now what we're going to do to figure out where that occurs, we take y sub r and we subtract 10 feet, right? Because all we do is work on the moment from this hinge. So we're going to go we're going to go from the top, we're going to come all the way down y sub r, but the hinge is at 10 feet from that reference location. So we subtract 10 feet from y sub r to get that line of action. And then the other one that we have acting, it's going to also be positive, is the weight acting at 3 feet, but we need only the y component. The x component. Let's see. So weight is acting down this way. I actually goofed this up and forgot to include the weight. So we want the component that's acting normal to the gate. So I'm just going to call this W sub x and multiply that by 3 feet. So my solution for this is actually incorrect because I didn't include the weight component here. So I'm gonna end it there. But basically, you would figure out your trig to know whether you're getting the cosine or sine of that weight component that would be normal to the hinge to include. Alexi, did you work through this by chance today with anyone?
I did the really similar one, but it's the other one with the wire at the top of the gate.
Oh yeah.
Not this one. I guess just to mention, I think A slide previously rounded to 2 sig figs, but it should be 1, I think, just because the 6 feet and the 10 feet are given in.
I didn't. So the 6 and the 4, so what I mentioned was the 6 and the 4 are given as 1. I decided to call that 2 because it gave us 24 because I didn't change this. Otherwise, I would have changed this to 20 and feed it forward. But because we were sort of doing this at the end, because this had 2, I decided that my answer could have 2. So just an FYI, I didn't go all the way back to square one on that. But.
Okay, and then I guess just relate to that, but then they should still round at the end, so they should keep that 6,860.
Exactly.
And only use that only round at the very end.
Round at the very end, and that's why you could use 24 instead of 6 or 4 as the determinant. Yeah, in this case. Yep. All right. Sorry for anybody who held on for an extra half hour. Thanks for sticking around. I hope that was useful to you. I'm happy to take any questions if you've got them. But that's all I had set up for today. Yeah, Emma, go ahead.
I just had a quick question about the weight force that you'd calculate later. So would you use like the gate over 2 for the distance when calculating the force? And then when you calculate where the force is acting, would you use the triangle rule 2/3 L?
So for the weight, if you mean the weight of the gate itself, the weight of the gate acts at 3 feet from either end. So it has to act at the centroid. You would not, and therefore you would use so what did we say? This is, oh, shoot. Sorry. Back. Let me change my pen color to blue real quick. If this is 60 degrees, the only thing you're going to do is figure out what component that is, some W sub X that's acting normal to it to give us the moment. So you wouldn't apply the weight down here at FR. It has to act at the centroid. So this has to be 3 feet.
Even for the sum of the moments?
So sorry, let me go forward. So the moment, I went too far. Yeah, so the moment here, oh gosh, I keep going out of pen mode, sorry. Right, so the moment that's in, that the weight applies is the X component. I'm calling it the X component that works normal. And then you multiply that by 3 feet. Not you don't do the 2/3 thing. Yeah.
Oh, and then just for the weight force, you just do the specific weight times the volume, right? Or no, you do.
No, we're given that it's 8,000 pounds, the weight of the gate.
Oh, okay, that makes more sense.
This isn't the weight of the fluid. Yeah, it's just the weight of the gate.
Okay, that makes sense. Thank you.
Sure.
So wait, would it be 8,000 times 3 times cosine of 60 since you want the X component of the weight?
Let's see, I hadn't gotten that far, but let me, we can go through that real quick. Let me think that through. So if this is 60, then this part's going to be 30, so that'll be 60 as well. And so, yeah, it would be, let's see, so the cosine of 60 is equal to WX over W. We know W, so yeah, WX is equal to W times the cosine of 60. Yeah, so that's correct, Emma.
Okay, thank you.
You bet. That's a different Emma. We have a lot of Emmas in class. All right. Great.
I had a question regarding the exam.
Okay.
So earlier in a recitation and on a written homework, we had a viscosity problem with a block sliding on an inclined surface. And just since there wasn't any of those in the review packet and they're a little more difficult than the viscosity problems we saw, is that something that we should prepare for?
Yeah, I mean, in the sense that it's not unlike this problem. It's just that you only had, I mean, you have one thing moving. You only had one layer of fluid in that case, right?
Sure.
So,
yeah.
Yeah. So it wouldn't be unlike this one. Yeah. I mean, I can't guarantee. I'd say be prepared. I can't guarantee you what you'll see, but
yeah, sure.
But yeah, it's worthwhile to be prepared for that.
Okay, sounds good. Thank you.
Sure.
I had a quick question on the one of the multiple choice problems.
Okay.
I can read it to you. It said there's multiple options. It said cavitation or boiling occurs when the absolute pressure in the fluid reaches the vapor pressure. Is that correct?
Yes.
Okay. Appreciate it. Thank you.
So that one is the cavitation or boiling occurs when the absolute pressure in the fluid reaches the vapor pressure and not the vapor pressure meets the atmospheric pressure. I thought it was E,
No.
but I guess that.
No, you if the pressure meets, you have to meet the vapor pressure. I guess I didn't think carefully about absolute or gauge. It's not about meeting atmospheric pressure. It's just about meeting your vapor pressure.
Okay. Okay, cool.
Thank you.
You bet. Take care, Abby. Anyone else? Mohammed, Dan, any questions?
Yeah, thanks. Appreciate it.
Bet.
So we'll just the exam's open 15 minutes prior towards class and then closes 15 minutes after class.
It ended up, so I'll make it available for a full 2 hours. You have whatever 90 minutes within that 2 hours to work on it.
Right
So
on.
it'll open up at 12:30 and it'll close at 2:30, and you have 90 minutes within that
Sweet.
120 minute window.
Sweet. Will you be on Zoom in case we have questions so we can shoot in there? And okay, cool.
Yep. Yeah,
Sweet.
I'll be on Zoom.
Thank you.
You bet. Take care. So, Alexi, I guess I didn't confirm this with you guys, but we'll plan to meet tomorrow before the exam at 11:30. Are you?
Yeah.
Time?
Yeah.
Okay.
Yeah.
Perfect. That sounds good.
I guess, does Mohammed have any questions?
No.
Are you there?
Any questions? May not be there.
I was about to I guess so. I've just finished grading the problem 5, and